Okay, can I start?
Go ahead.
So can I start? Oh, okay. Okay, I didn't see your thumb up. Okay, welcome to today's seminar. So it's my great pleasure to introduce our speaker today, Dr. Joel Ong. Joel is got her PhD from Yale University, supervised by Professor Sabani Basu. And then he got her NASA Hubble Fellowship at the University of Hawaii. And he worked at Hawaii for maybe 3 years. And then he moved to University of Sydney and got his ARC DECRA fund this year. So, and Joe's research focused on the theoretical part of asteroseismology, especially on the rotation, magnetic fields of mixed modes in red giant stars. Okay, Joe, it's your time to go ahead with your talk.
Thank you, and it's a pleasure to speak to you today. I'm going to talk to you a large part about stellar rotation and magnetism as sensed through asteroseismology. And the particular kind of asteroseismology through which the sensing is done is that of solar-like oscillations. Now, I say solar-like because it might be a surprise to some of you. The sun is a variable star. It is the prototype for this entire class of variable stars. If you were to take a time series of images of the sun, like this one, or a time series of disk integrated radial velocities, like the kind shown here, right? If I were to integrate over the disk, you would see motions caused by, convection in the outer layers of the star, of the sun, right? And these convective motions then result in sound waves, pressure waves, that travel throughout the solar interior and yield normal modes of oscillations when they interfere with themselves constructively. So the way this works is that you would assemble a time series of either disk-integrated brightnesses or radial velocities, the latter shown here. And in the frequency domain, such a time series yields a Fourier power spectrum that has the morphology of many peaks. Each one of these peaks is a normal mode of oscillation, and they can be seen to form a repeating pattern characterized by standard overtone spacing, which we call delta nu sometimes, or a frequency of maximum power, which we refer to as nu max. Now, there are many nice things about solar-like oscillations that render them particularly fit for purpose for studying stellar interiors and structure. But I think at a high level, in a high-level sense, it suffices to know that a large fraction of everything we know in astrophysics is built on an understanding of stellar astrophysics, and most of stellar astrophysics relies on studying cool stars like the sun. Right. And so in this sense, asteroseismology is particularly important, being our only direct observational probe of stellar interiors. So in seismology, it's customary almost to show a Hertzsprung-Russell diagram with patches overlaid on it like this. This is called an asteroseismic Hertzsprung-Russell diagram. And each patch here shows a different class of variable stars. For today's talk, I'll be focusing on what would appear to be a narrow strip of the Hertzsprung-Russell diagram. And these correspond to cool solar-like oscillations. But looks can be deceiving because most stars are cool stars like the sun or less massive stars. And so it transpires that most stars also are solar-like oscillators. And this being the case, the study of solar-like oscillations then becomes important in the sense that it is almost universally applicable to stars in general. Okay, so most of the observational data that we obtain about solar-like oscillations has come from a select few space missions like Kepler, TESS, and before that, CORO and MOST. And because it's been relatively easy to measure solar-like oscillations through the use of space photometry, seismology has come to prominence in recent years as a tool for prosecuting stellar astrophysics. And the tool can be applied in several ways, of several degrees of sharpness or bluntness as your needs might require. So if you're able to measure the large separation and Umax alone, for example, we can employ what are called scaling relations in conjunction with, say, a spectroscopically measured temperature to estimate the mass and radius of stars in general, right? And this is the capacity in which I would argue the seismology of solar-like oscillations has been most broadly applied in the sense that it is easiest to measure delta nu and Umax and no other quantities from a star's power spectrum in photometry. And therefore, delta nu and Umax seismology has been applied to the most stars. However, it's also possible to include some understanding of stellar astrophysics into our seismic constraints. So if you were to construct stellar models to match asteroseismic constraints, then you can use the model, the information that you input into the models to, in addition to constraining the mass and radius of a star, also constrain its age. Right? And so it is in this capacity that asteroseismology will soon be very widely employed for the purpose of the Roman space mission. And indeed, if we were to supplement delta nu and Umax with information about individual frequencies of oscillation, our constraints on stellar properties and on ages in particular become extremely precise. Right? And through this technique, seismology has become a most precise technique for measurements of masses, radii, and ages of few stars. But all of this fundamentally is model dependent, and while all models are wrong, some are useful. Seismology can also be applied in the sense of measuring things, measuring how your models are wrong. Right? So the most common way in which this is done for, say, the sun is to measure how the sound speed and density of the true sun differ from your model. And in this fashion, you measure the sound speed and density of the star in a model independent fashion, right? So what we're going to do today is none of these things, but I thought I would give you a rough overview of other ways in which seismology has and can be applied. Today, however, we'll be focusing on rotation and magnetism. And in order to understand the observational morphology that we're going to exploit, I'm going to have to rearrange the observational data into a form that makes it easy to reason about all of these normal modes. So given a power spectrum, what we can do is that we can exploit the regularly repeating pattern given to us by the overtone spacing in the following way. We could phase fold the power spectrum by breaking the power spectrum down into chunks, each of equal width, delta nu, and then rearranging these chunks and increasing order of frequency from bottom to top. When presented in this fashion, the power spectrum has the appearance of some kind of three-dimensional object, which you will look at from above. This is called an Eschel power diagram, or an Eschel diagram if you're looking at just the individual mode frequencies having fitted peaks to the power spectrum. Now I'm going to have you look a little closer at this Eschel power spectrum. You will see that they take the appearance of vertical ridges, right? Each ridge corresponding to modes of a different angular degree L. So here are the radial modes, L equals 0. Here are the dipole modes, L equals 1, and so forth. If you look more closely at the Eschel power diagram, however, you see that each of these ridges has a different shape. The radial modes form a ridge where each peak in the ridge is a single peak. The dipole modes actually give you two peaks per order in the ridge, the power spectrum. The quadruple modes give you three peaks, and so forth. So something is clearly going on that distinguishes the different angular degrees L from each other. And that something is rotation. So the way this works is that in the absence of any azimuthal or indeed spherical symmetry grading, all modes of the same L and different M pulsate at the same frequency, right? And there's a different multiplicity for each L, which you probably learned about in your high school quantum mechanics class. And what happens in a rotating star is that spherical symmetry is broken, although azimuthal symmetry is preserved. In the presence of rotation, then, modes that propagate in a prograde sense relative to the rotational axis will appear to pulsate more rapidly than modes which propagate in a retrograde sense relative to the rotational axis. The inclination angle of the star's rotational axis relative to the line of sight also determines which modes appear to pulsate when integrated over the visible disk, and which modes are geometrically cancelled out so that you don't get any intensity variations or radial velocity variations. The observational effect of this is that rotation turns a single peak in the power spectrum into a multiplet of peaks, with the width of the multiplet being determined by the rotation rate, the number of components in the multiplet being determined by the degree L of the mode, and the inclination angle of the rotational axis determining how power is distributed between multiple components. And this is why we saw different peaks, different multiplets in the power spectrum having different number of components depending on the degree L earlier. So all this is to say that rotation can be measured from asteroseismology, right? And rather than looking at things peak by peak or multiplet by multiplet, it also might pay to build some intuition for how things look like on a phase-folded frequency shell diagram, right? Rotation turns a single ridge into a multiplet of ridges, right? With the relative visibilities of different components being determined by the inclination angle of the star's rotation axis. So what we saw earlier was the sun being seen equator on, but you could infer the inclination angle of the stars other than the sun in this fashion. Okay, so that's enough talk about rotation and the sun and solar and sun-like stars. What we deal most often with in an observational data set is not a sun-like star. And the reason for this is that owing to rather nasty details of the observational selection function imposed on us by Kepler and then also TESS, most stars that we have observational access to with regards to solar like oscillations are by no means sun-like stars. They tend instead to be evolved stars like red giants, so classical pulsators. And red giants in particular heavily dominate our asteroseismic sample. Now, the problem is that the observational morphology of a red giant's normal modes is very different from those of a sun-like star. Here, I show a shell diagram for a sun-like main sequence model, and what I'm going to do is I'm going to play an animation demonstrating how the mode frequencies evolve on such a diagram as we step off the main sequence and head up the red giant branch. Right? As this evolution occurs, you can see that the orderly pattern of pure P modes, which would otherwise form vertical ridges on the shell diagram, is disrupted by a forest of additional supernumerary modes, and these interact with the pure P modes in a rather complicated fashion. Okay, so what's happening here is that these extra modes are G modes, which satisfy a different relation than the P modes, whereas the P modes have a uniform overtone spacing and frequency. The P modes have a uniform or undertone spacing and period. And these two families of modes coexist in the same star and couple to each other in a nonlinear fashion. And it is this nonlinear coupling that makes things very difficult to model and very difficult also to apply techniques originally developed for use with the sun to stars that are not like the sun. So what's happening if I were to examine this nonlinear coupling in detail is that over the course of stellar evolution, the frequencies of pure P modes decrease over time, and the frequencies of pure G modes increase over time, right? And if we were able to track the notional power spectrum of a star as it evolved over time, we might then expect to see these frequencies crossing every time a P and G mode share a frequency. In a real star, however, as we will shortly examine, these two kinds of modes couple to each other. So there is coupling between the P and the G modes, and it is this coupling that produces the phenomenology of what's called an avoided crossing, where over the course of evolutionary time, whenever a P and a G mode encounter each other, right, they avoid each other in such a way that a G mode smoothly becomes a P mode, and a P mode smoothly becomes a G mode through this kind of long-range exchange of character. Right? And they're called avoided crossings because if you unwrap this animation to show time on the horizontal axis, you will see that the P modes and G modes evolve along different families of curves. So the units of this diagram are intended to show the P modes evolving on straight lines from left to right, whereas G modes are frequencies that increase over time as the green curve here. The actual oscillation frequencies that we have access to are depicted with the blue curves, right? And they interweave between the two families of P-like and G-like mode frequencies, and they trace these families out, except where the two families of curves cross, at which point the mixed mode frequencies avoid the loci of crossing, hence the name avoided crossings. So it is these mixed modes, these avoided crossings, as exhibited by mixed modes, that make life quite difficult for us as people who wish to interpret what we see in terms of quantities that exist in stellar models. So in order to better understand what this coupling is and how it works, I'm going to unfortunately have to step aside from observational data and do some theory. So generally speaking, we describe these normal modes in stars as waves, and the waves must satisfy a wave equation. The wave equation that governs waves in stars is quite complicated. So let's start with a perhaps simplified description of waves. This is a wave equation that you might have encountered in undergrad physics, for example, and it describes the propagation of sound waves, described with a sound speed, in a homogeneous and isotropic medium. So the sound speed does not depend on the direction of the waves travel, nor does it depend on where you are in the medium. If these properties are satisfied, then you can just Fourier transform both sides of the equation in space and time to yield something that looks like this, right? Where you have on one hand, you have the frequency of the wave squared multiplied by the Fourier transform of the wave itself. And on the right-hand side, you have the wave number, which is 1 over the wave. And so it turns out that such a relation doesn't actually depend on the wave function itself. And this gives you a relation between the frequency of the wave and the wavelength of the wave. This is called a dispersion relation. Now, in a more complicated medium, for example, where the sound speed does change with respect to where you are in the medium, the wave equation is also then modified to yield, in most cases, a cutoff frequency term, which I've depicted as omega squared acoustic cutoff here, right? And you can't do the same thing anymore, right? But you can pretend you can do the same thing by still taking a Fourier transform with respect to space. On the right-hand side, you can pretend that whatever function of position you have is a local wave number. And this gives you a discriminant for whether the wave is propagating or decaying wherever you are in the medium. So to illustrate this, I've made what's called a propagation diagram, where here I show the acoustic cutoff frequency, right? And the way you would read this diagram is that this cutoff frequency is a kind of potential function in a Schrödinger-like wave equation. And the frequency are the energy eigenvalues in this equivalent Schrödinger problem. So the way you would read this diagram is that if you have a wave at a particular frequency, here I've shown one such frequency with a horizontal line, then that wave can propagate in regions of the diagram that are shaded, and it will also then decay in regions of the diagram that are not shaded. Right? So the wave function then will look like this. Right? In reality, of course, if your medium is quite complicated, then potentially you could have multiple regions in which the wave propagates, separated by thin layers. And in those layers, you might remember from your high school quantum mechanics, a wave that passes through an evanescent region between two propagating regions will decay exponentially. So the situation with mixed modes is kind of similar, except we have an even more complicated dispersion relation, the terms of which you don't really need to care about, but we have now two different shaded regions corresponding to two different kinds of waves. At high frequencies, we have waves with which we are most familiar. We have pressure waves, sound waves, the kind that I'm making, and which are being transmitted to the microphone. And at low frequencies, we have gravity waves, right? Which are more kind of the waves that you would see on the surface of a body of water like a pond. And these two kinds of waves it turns out, can propagate at similar frequencies in different parts of a star. And in particular, they can do so at frequencies close to Numax, which is the frequency at which we observe these waves at all. So in a red giant, then, it is possible for waves of mixed character, of normal modes of mixed character to exist, which behave like G modes, gravity waves, in the center of the star, and like pressure waves, E modes, and the outside stuff. So traditionally, the main ways in which we attacked or described these waves were either through brute force numerical calculations with no regard for physical insight, or else through a purely qualitative WKB-like approximation to describe the overall qualitative features of the waves, but without the capability for making well-defined numerical predictions. So I'm going to walk you a little bit through a quantitatively suitable formalism that I described during that I derived during grad school, that has turned out to be extremely productive for describing both the qualitative behavior of these waves and also for making quantitative predictions. The main approach we're going to take is borrowed in large part from the field of quantum chemistry, where we describe molecular orbitals as linear combinations of atomic orbitals, right? And it turns out that there is a well-defined asteroseismic analog. So I'm going to walk you through how the quantum mechanical version works, and then walk you through also how we steal it for seismology. In quantum mechanics, right, in particular in quantum chemistry, we are concerned with how to describe molecules, assuming we know how atoms already work, right? So let's say we wish to construct a hydrogen molecule out of two hydrogen atoms. The first thing you would do is ask, what do the energy eigenvalues and wave functions of the hydrogen atom look like, right? And you can solve for this because you learn how to do this in your second quantum mechanics class at university, right? And having answered that, you may then ask, what do the energy eigenvalues and wave functions of two hydrogen atoms look like, assuming they don't talk to each other? And you know the answer because all atoms are similar to each other. So the eigenstates and eigenvalues of two atoms are just two copies of the energy eigenvalues and eigenstates of one atom, just in the abstract. Now, what's going to happen is that as you bring, you can treat these two isolated atoms as being a single molecule, but with an infinitely large interatomic separation. And what's going to happen as you reduce the interatomic separation is that you will find that the ground state of the combined system is the ground state of the two atoms interfering constructively. And the first excited state of the combined system is the ground states of the two atoms interfering destructively, right? So we can see that the ground state is them interfering constructively, and the first excited state is the two ground states interfering destructively. There is an avoided crossing hidden in this construction as well, in the sense that if you were to generalize this to hydrogen-like atoms, parameterized by a charge ratio, then the ground states and the first excited state execute an avoided crossing associated with the ground states of the two atoms. Right. So in general, if you were to have a combination of atoms, combination of atomic orbitals, right, out of which you construct a single molecular orbital, the coefficients of these linear combinations of atomic orbitals can be found as the eigenvalues for a generalized emission eigenvalue problem, where you solve for the eigenvalues and eigenvectors of these matrices whose elements are composed of overlap integrals between the atomic orbitals, right? And the eigenvectors give you these linear combinations of orbitals, of atomic orbitals. The eigenvalues then give you the energies associated with these molecular orbitals. So the situation in asteroseismology is entirely analogous, right? It is possible to describe these mixed modes as emerging as being the solution to some boundary value problem described by a wave operator associated with the stellar structure. Now, it is also possible then to decompose this wave operator into a P-like wave, into a G-like wave operator that gives you pure G-mode solutions with a small remainder term, and also a pure P-mode wave operator that gives you pure P-mode solutions with a different remainder term. And once you are able to construct these wave operators, you can just turn the crank on exactly the same mathematical machinery. You would describe mixed mode of oscillation as a linear combination of a pure P mode and a pure G mode, with the coefficients of this linear combination being found as the eigenvectors of a similar generalized emission eigenvalue problem, and with the eigenvalues of this generalized emission eigenvalue problem being the frequencies of these mixed modes of oscillation. So that's all well and good in the sense that that allows us to A, perform calculations for maximum frequencies, and B, to describe in a qualitative sense how these mixed modes correspond to notional fictitious pure P and pure G modes. Now, why do we go through all this trouble? Now, it turns out that this also allows us to perform some kind of inverse problem, right? Where this gives us access both to the pure P modes and the pure G modes of the kind that we would otherwise not be able to measure directly. So this assists in our ability to disentangle, right, the pure P modes and pure G modes given an observational set of X modes. Now I'm going to do a bit of a detour here, and I showed you how rotation modifies the pure P mode frequencies on a shell diagram, right? I earlier mentioned that pure G modes satisfy a different eigenvalue relation, and that rather than being uniformly spaced in frequency, they are instead uniformly spaced in period. So in principle, it is then also possible to construct a phase-folded power spectrum in the period coordinate rather than in the frequency coordinate, right? And that would also then give you vertical ridges of exactly this, of a similar kind, where each horizontal line on this figure now gives you a different G mode rather than a different P mode. Now, what rotation is going to do is that it's going to split all the G modes non-uniformly in the period coordinate because the splitting is done uniformly in the period coordinate. And so rotation turns G modes into, rotation turns a G mode, a shell diagram, into a multiple of ridges, like it does a P mode, a shell diagram, but the ridges are now curved as a consequence of the overtones being constant in period rather than frequency. Okay. So if you were to actually construct a period a shell diagram from an observational power spectrum, it would unfortunately not look like that, right? This is what you would get instead. And again, that's because we are not directly able to measure the mode frequencies of pure P or pure G modes, only mixed modes. Now, it turns out, however, that with some understanding of the mechanics behind mode coupling, we can undo the mode coupling to infer the pure G mode frequencies. That's what I'm showing here. So this is what's called a stretched shell diagram. And you can basically see that the morphology of such a stretched diagram is more or less identical to what you would predict analytically if you had access to pure G modes. So that allows you then to read off the core rotation rate, because the G modes propagate in the core, directly from diagrams like this one made from observational data. So it is through techniques like this that we now have measurements of core rotation rates in red giants for thousands of red giants, right? The core rotation rates are not something we can measure even in the sun. So this is something really, really special. And Gang has played a major role in improved measurements, of which I'll talk more about later. But just keep this in mind for the moment. Now, so far, the discussion of G modes has focused on core rotation rates, right? And what Gang has done is going to be related but not quite the same. However, observationally, we don't have access to pure G modes, like I've been saying a while now. What we do have are mixed modes, and these mixed modes respond to rotation, again, in a more complicated fashion than pure P or pure G modes might. So rotation turns single peaks into multiples of peaks in the absence of mode coupling. And again, time evolution causes the centers of these multiplets to evolve over time. What coupling between the P and G mode cavities does is produce multiplets of mixed modes where the positions of each multiplet component are all separately undergoing avoided crossings, right? And it is these really complicated avoided crossings that are really difficult to describe using conventional approaches to mode coupling, such as this given to us by asymptotic theory. So these avoided crossings are sometimes referred to as near degeneracy effects. And it turns out that if you were to neglect these near degeneracy effects, you would systematically misestimate your core and envelope rotation rates. In particular, it turns out, as shown in this paper by Felix Osborne last year, that the measurement error you incur in measuring the core rotation rate is systematically negative. You will systematically underestimate, and it's going to be of the same magnitude in absolute terms as the measurement error you incur in the envelope rotation rate. And this makes measuring envelope rotation rates really hard because in a red giant, the core is rotating fast and the envelope is rotating slowly. And so if you make the same amount of if you make some relative measurement error of a few percent in measuring the core's rotation rate, that's fine for the core's rotation rate. But the same absolute measurement error in the envelope rotation rate is often larger than the entire envelope rotation rate. So shout out to Li Gang, who did a more principled measurement of a large number of envelope rotation rates in these red giants. I've shown the results of his observational census of core and envelope rotation rates here, with core rotation rates on the horizontal axis and envelope ones on the vertical axis. Right? And I remove points for which the envelope rotation rate is not statistically different from zero. Even for those envelope rotation rates which have been measured to be statistically distinct from zero, you can see something interesting, right? These rotation rates are measured in the sense of having the core define the direction of the rotation axis. And while the vast majority of stars do have envelope rotation rates that are positive with respect to the core, there is a non-trivial subpopulation which possess negative envelope rotation rates. And that suggests a core and envelope that are counter-rotating, which is not something you would ordinarily expect to emerge from the standard stellar evolution. Why would the core and envelope be rotating in opposite directions? However, if we were to entertain the possibility that the core and envelope could be rotating in opposite directions, it behooves us also to consider the possibility that they might just be rotating around different axes altogether, right? With counter rotation being the most extreme example of a misalignment in the rotation axis. So that brings us to my next topic, which is the potential for geometrical differential rotation, where not just the rates of rotation, but the direction of the rotational axis can vary as a function of position of the star. So aside from the obvious observational anomalies, there are other reasons why we might wish to consider this. Here's a figure from Simone Albrecht's paper on spin-orbit misalignments in exoplanet systems. So the arrows here show the direction of the planetary angular momentum the direction of the stellar angular momentum vector relative to the planetary orbital angular momentum vector, shown as the y-axis in this coordinate system. Most stars tend to be spin-orbit aligned, right? And that's shown by a clustering of points near the y-axis. But there's a preponderance of planetary systems where the spin axis and orbital axis of the spin axis of the star and the orbital axis of the planets are misaligned by quite a lot, right? So these points that are not clustered around the y-axis tend to be distributed instead around the equator. There's also the possibility that stars and planets could interact, right? For example, if a star eats a planet on such a misaligned orbit, then the angular momentum of the misaligned planet is going to be deposited into the envelope first, right? And it takes some time for angular momentum to be transported within a star, which means that there's a real astrophysical possibility that different parts of the star could actually possess different rotational axes. So how would we describe this in at least a theoretical sense? Well, in a two-zone model, what we could do is assign an angular momentum vector to the core and the envelope separately. Right? The direction of these vectors I've shown in this diagram with omega vector for the core and omega vector for the envelope. Now, for an observational parameterization, we don't tend to work with vectors. We tend to work with single parameters, right? And so these are parameters. These are parameterized by the core inclination angle and envelope inclination angle and an internal orientation angle, right? Which all three together specify the misalignment angle theta between the core's angular momentum vector and the envelope's angular momentum vector. So some of you might have seen me glibly gloss over this stars and Newcastle. Unfortunately, I don't really have a choice but to do that again to keep within time constraints. So we could go more into detail about this during questions, but I'm fortunate to have skipped the theoretical nitty-gritty. The observational effects of having misaligned core and envelope is that earlier we already established that the distribution of power between multiple components in the power spectrum is determined by the star's rotational, the orientation of the star's rotational axis. If the envelope and core were permitted to have different orientations for their rotational axes, then what could well happen is that you could have multiplets that are more associated with p modes in the envelope having different multiplet component visibility ratios than multiplets which are associated with g modes propagating in the core. So this would be a smoking gun signature of misalignment between the rotational axes of the core and envelope in a real star. So I bring that up because in some way this has already been seen. So again, this might be familiar to some. Kepler-56 is a star that is known to be peculiar in many ways, right? It is rapidly rotating in Kepler photometry, but what made it famous, at least in the Kepler days, was the fact that it was a multi-transiting spin-orbit misaligned stellar system. That is to say that there were multiple transiting planets, all of whose orbits are misaligned from the rotational axis of the star. What's remarkable about this is that none of this should be the case. First, Kepler-56 is a very cool star. Cool stars are magnetically braked and therefore should not be rapidly rotating in the first place, especially not this fast, this far up the red giant branch. Kepler-56, also being cool, should not be spin-orbit misaligned because spin-orbit realignment is thought to be especially efficient in stars that are cool. It especially ought not to be spin-orbit misaligned with multiple mutually aligned planets. There are only 5 other planetary systems for which this has been seen, and none of them are as cool as Kepler-56. They're all main sequence hot stars. So if you look at the power spectrum and the asteroseismology of Kepler-56, you do see such a signature of different multiplets having different visibility ratios, like the kind we've shown previously. And this tells us that it is quite likely for different parts of Kepler-56 to be rotating around different axes. So you can turn the crank on your inference machine and make an inference in the form of posterior distributions, right? So the dashed curves here show the old attempts to fit the inclination angles of the core and envelope separately without all this nonlinear matrix machinery. And the solid curves show the revised distributions with a better understanding of mixed modes taken into account. And from this, it is clear that the implied envelope rotation axis of Kepler-56 does point in a different direction from that of its core. This is like 4 sigma significance. Anyway, so what does this mean? The most likely interpretation of what we're seeing is that it is quite likely that the envelope of Kepler-56 has efficiently realigned itself with the orbits of its planets, while the core retains some memory, potentially, of an earlier solid body rotational orientation. But this also doesn't resolve all the questions we have about Kepler-56, right? It resolves everything to do with spin-orbit misalignment by just making it go away, but it doesn't tell us how Kepler-56 remains rapidly rotating. And it leaves us with a further question as to for how long such a very unusual internal rotational profile could potentially exist, or whether it's even astrophysically possible to emerge from single-star evolution. So the most obvious explanation for Kepler-56 is, of course, if it were the result of something not to do with single-star evolution, like the star having eaten a previous inner planet that no longer exists. However, it turns out that the in-spiral for a planet placed interior to its 2 existing planets is not sufficient to explain all of the angular momentum that Kepler-56 contains. So here I show possible trajectories for in-spiral for candidate planets placed closer in, right? And these are colored by different values of the tidal quality factor Q. Now, these correspond to different amounts of magnetic rotational braking required to explain Kepler-56's rotation today, right? And it turns out that even with extremely aggressive magnetorotational braking and unphysically aggressive in-spiral, you would require in most of these scenarios, you would require Kepler-56 to have been rotating at a very large fraction of its original breakup velocity on the main sequence in order to present the kind of rotational features that it does today, right? And so rather than having the envelope spun up by tidal torquing, it is rather more likely that this signature was produced by a planetary engulfing at some point in the past. Okay, so far I've been talking about rotation, and I did promise to talk also a little bit about magnetism, although I realized I only have 10 minutes to do this in, so this is going to be a bit of a speed run. But another astrophysical question we can tackle with access to mixed modes is the question of magnetic fields in stellar interiors. In stars like the Sun, the most we can do about magnetism is measure its features at the surface. But with access to G modes, we can also measure magnetic fields in the inside of the star. So here's the period Echelle diagram again, showing how multiplets respond to rotation. Right? In a magnetic star, what's going to happen is that in addition to this rotational splitting, which you can see is symmetric around n equals 0, we also have an additional asymmetric component arising from magnetism. And that's this slide over here that causes the multiplet to become asymmetric depending on the strength of the magnetic field. In fact, if the magnetic field is really, really strong, the asymmetry can be so large as to interchange the ordering of multiple components in the observational power spectrum. Now, we actually do see such asymmetric splittings in observational power spectra. Again, Li Gang is the preeminent observer here with the original Nature paper discovering magnetic fields in the cores of red giants. And in the years that have followed, technique development has progressed to such an extent that we're now able to reason and reasonably discuss population level differences in the strengths and distributions of red giant magnetism. Now, of more theoretical interest, however, to me at least in some way, is how we relate these observed asymmetric splittings to magnetic field strengths as shown here. Most approaches rely on the weak field limit, where you assume that the magnetic field is so weak that you can apply linear perturbation theory. And I'm going to go over a little bit of work done by Nicholas Gray, formerly a grad student at Caltech, now a Hubble Fellow at Princeton, describing in a more rigorous mathematical fashion how we would go from field strengths to asymmetric splittings and back. The way this works is that if your magnetic field is strong enough, it will actually deform the eigenfunctions that you require to describe your normal modes with. So ordinarily, we use normal modes that are described in the horizontal direction by the spherical harmonics, right? And the spherical harmonics, in turn, are products of some complex phase in the azimuthal direction and associated Lagrange polynomial in latitudinal direction, right? And these are associated with what are called tidal eigenvalues, which in most cases are just L times L plus 1. What Nicholas showed is that in the presence of both rapid rotation and or strong magnetism, it is these tidal eigenvalues which deform, and that gives you asymmetric splittings as well. So I'm going to skip all this because I don't have time. But at the end of the day, what this gives us an avenue to is an avenue also to understanding the limiting behavior of these normal modes in the limit at the field strength gets very large. I'm showing in these contour plots the values of these tidal eigenvalues for different L and M. And what you can see is that in addition to the actual tidal eigenvalues, there are parts of the plot that are empty. They're shown here with pink cross hatching. These correspond to when the field is so strong that these tidal eigenvalues, which would be L times L plus 1 in a non-magnetic star, actually become complex. Once that happens, you cannot sustain a normal mode in the horizontal direction, and the modes then become suppressed. They disappear from the observed mode set altogether. So that's a pretty interesting result that emerged from this kind of advanced mathematical analysis. Another thing a field can do is that if the field is strong enough, it can magnetically confine pulsations. So this is easier to see at large angular degree, right? Ordinarily, we would assume that the pulsations occur around the same axis as that given to us by rotation. If you have a dipole field that is strong enough, however, it dominates the dynamics and it dominates the symmetry breaking in such a way that the normal modes then pulsate around the magnetic axis, which in turn also slowly rotates, right? And I'm going to give you some time to stare at this cool animation before I move on. But you can see, for example, most easily from the m equals plus and minus 3 modes here, that the pulsations are occurring around a different axis than the rotation one. And you can see the pulsation axis itself being rotated. Observationally, what this does is introduce another level of complexity. So here I show the m equals 0, minus 1, and 1 modes for a very magnetic stuff, where the ordering of the multiple components has been interchanged because the magnetic field is so large. I'm going to vary the inclination angle beta now, the obliquity angle beta now. And what you should see happening is that each of these multiple components associated with different n, in turn further splits into a multiplet associated with the oblique pulsations. So rather than 2L plus 1 different multiple components in the presence of rotation, strong magnetism, strong enough to confine the modes around the magnetic axis, yields 2L plus 1 squared components. So this gives us 9 possible dipole mode frequencies and 25 possible quadruple mode frequencies. So the complexity quickly gets out of hand and makes life very difficult. The hardest part of this for observers potentially is figuring out which modes you see correspond to which modes you compute. This is called the mode identification problem, and it's still in general unsolved, but it becomes really, really messy when you have this many modes to identify. So one thing that Nicholas and I realized is that you could exploit the complex amplitudes of your Fourier transform to assist you in this mode identification. Ordinarily, when we do seismology, we take a Fourier power spectrum, which is the absolute value squared of the Fourier transform. But when we analyze only the Fourier power spectrum, we're actually throwing away information encoded in the phases of the Fourier transform. What Nicholas and I showed is that if you were to do a complex cross-correlation between different parts of the power spectrum, you are able to identify which peaks you see in the power spectrum correspond to which modes, correspond to modes of which m. For example, if you were to do a complex cross-correlation of the power spectrum against this window of the power spectrum, you will see peaks in the cross-correlation function implying that these 3 peaks correspond to the m equals 0 mode, for example. Right, so that's cool. Another thing that we've been looking at is the possibility of describing mixed modes with a similar level of rigor and precision as we do without magnetism. Right. So this is work that one of my undergrad students, Kiri Ma, has been doing over their summer research project, and we are in the process of cleaning and writing it up. But here's a sneak peek. Here's a spectrum of mixed modes in a simulated red giant. And as we vary the simulated obliquity angle, again, you get a complex forest of additional peaks, each separately undergoing avoided crossings. The way in which you describe these avoided crossings is pretty non-trivial. It requires some really advanced mathematics called Fourier theory, but this is very impressive for an undergrad, and I would say he has been the most motivated undergrad I've ever had. And finally, one other thing that's still cooking is the potential for just abandoning a dipole field altogether. So Nicholas has done some work recently on simulating the kinds of horizontal eigenfunctions you would get with arbitrary monotic configurations. That's very much work in progress. Anyway, to wrap up. So in the first part of my talk, I showed that you could describe mixed modes of oscillation as, roughly speaking, acoustic molecular orbitals being combinations of P and G modes in the same way as molecular orbitals are combinations of atomic orbitals. We then use this to extend our existing treatment of rotation, right? And apply this extended treatment to Kepler 56. And this application yielded the observational result that its core and envelope were rotating around different axes. And finally, I've gone over some, very, very quickly gone over some of the work that my collaborators and I were doing about using these mixed modes also to characterize magnetism and oblique pulsations. So that's all I have. Here's my summary slide, and I'll be happy to take questions.
I will pause the recording for now so everybody can ask questions and not feel pressured for it to be broadcasted.
Yeah.